So this one is about invertebrates. The first group are porifera. They're sponges. So sponges are basal animals that lack true tissues, and they belong in the porifera phylum. In the concepts, it says, lacking tissues and organs, how do sponges accomplish such tasks like gas exchange, nutrient transportation, and waste disposal? So they are filter feeders. So sponges will filter out food particles suspended in the surrounding water as they draw it through their body, and which in some species resembles like a sac perforated with pores. Water is drawn through the pores into a central cavity called the spongicle. I'm not sure if I'm pronouncing any of these words right. Spongicele. And then it flows out of the sponge through the larger opening called the osculum. Sponges may not have true tissues, but they do contain several different types of cells. And the lining the interior of the spongicele are flagellated choanocytes. Okay. These engulf bacteria and other food particles by yes. Yeah, I don't think I know how to pronounce a single word in this whole chapter.
It's weird because we don't deal with these organisms very often.
Yeah. So gas exchange and waste disposal. The body of a sponge consists of two layers of cells separated by a gelatinous region called the mesophyll. Because both cell layers are in contact with water, the processes such as gas exchange and waste removal can occur by diffusion across the membranes of these cells. Other tasks are performed by cells called amoebocytes. These cells move through the mesophyll and have many functions such as digesting and carrying nutrients, manufacturing tough skeletal fibers, and are even capable of becoming other types of sponge cells. And it's just a graph of what it is. So with that example of the large sponge, this would be like one of those little branches coming off. So there's your mesophyll, you've got your epidermis, and your other stuffs. And then, so right here, you got it over here, and this is how it's bringing in nutrients, and that's how it's pulling that all out from the water. Cnidarians? Okay. They are an ancient phylum of eumetazoans. So these are jellies, sea anemones, corals, hydras, and so on. The body plan and the two major variations is the focus. So the basic body plan is a sac with a central digestive compartment called the gastrovascular cavity. A single opening to this cavity functions as both the mouth and the anus. There are two variations of the body plan, a polyp and a medusa. So polyps are cylindrical forms that adhere to the substrate by the bottom of their bodies and extend tentacles waiting for prey. So those are like hydras and sea anemones. And then your medusa resembles a flattened mouth-down version of the polyp, and it moves freely in the water by a combination of passive drifting and contractions of its bell-shaped body, so like your jellyfish. Some exist as one or the other variety, while others can have both in their life cycle, so they can exist as polyps and medusas or one or the other. They are predators that often use tentacles arranged in a ring around their mouths to capture prey and push the food into their gastrovascular cavity, where their digestion begins. The tentacles are armed with batteries of cnidicites. These cells are unique to this group that function in defense and prey capture. So the specialized cnidae called nematocysts They contain a stinging thread that can penetrate the body wall of the prey, and then other kinds have long threads that can stick to or entangle small prey that bump into tentacles. So this is just what it looks like at rest, I guess. Or there's the short part, and then these over here are the thread that can go and penetrate through the prey wall, and they can go up. And then, if I remember correctly, it's the long thread that like releases a lot of poison, and then that's what causes your stinging sensation if you get stung by a jellyfish. Oh. Lophotrochozoans. These are a clan identified by their molecular data, and they have the widest range of animal body forms, spanning 6 diverse phyla: flatworms, rotifers, ectoprocs, brachiopods, mollusks, and annelids. Flatworms live in marine freshwater and damp terrestrial habitats. Since all of their cells are close to water, flatworms have no organs specialized for gas exchange, and their relatively simple excretory apparatus functions mainly to maintain osmotic balance with their surroundings. This apparatus consists of proton phrydia, networks of tubules with ciliated structures called flame bulbs that pull fluid through branched ducts opening to the outside. Most flatworms have a gastrovascular cavity with only one opening.
That's protonephrodite. No.
Oh, okay. I was looking up at the top. I thought that's
No.
proton. Yeah. Okay. Rotifers. These are tiny animals that live in freshwater, marine, and damp soil habitats. In contrast to the cnidarians, the last group. I don't remember. Cnidarians. And flatworms. Rotifers have an alimentary canal, a digestive tube with 2 openings. So behind the mouth, they have jaws called trophy that grind up food, mostly microorganisms in the water. Ectoprocs and brachiopods are known as this group because they have a crown of ciliated tentacles around their mouth called lophophore. As the cilia draw water toward the mouth, the tentacles trap food particles in the water. Ectoprocs are colonial animals that superficially resemble clumps of moss. The colony is encased in a hard exoskeleton studded with pores where the lophophores extend. In the sea, they are most widespread and numerous. They don't really move around. Animals and several species are important reef builders. They can also live in lakes and rivers. Brachiopods are colonial animals that superficially resemble clams and other hinge-shelled mollusks, but the 2 halves of the brachiopod shell are dorsal and ventral rather than lateral like in clams. They are only marine and live attached to the seafloor by a stalk, opening their mouths to allow water through their lophophore. And mollusks. The majority are marine but can inhabit fresh water. All mollusks are soft-bodied and most secrete a hard protective shell. Slugs, squids, and octopuses have reduced internal shells or have lost their shell completely during evolution. All mollusks have a similar body plan with 3 main parts: a muscular foot used for moving, a visceral mass containing most of the internal organs, and a mantle, which is a fold of tissue that drapes over the visceral mass and secretes a shell if there's one present. In many mollusks, the mantle extends beyond the visceral mass, producing a water-filled chamber, the mantle cavity, which houses the gills, anus, and excretory pores. Many feed using a strap-like a strap-like organ called a radula to scrape up food. So you can see your mantle cavity, there's the anus, and then you have your muscle foot and the digestive tract, your shell, and then there's the radula. So you can see the little rough parts that will bring food up into its mouth. Annelida are segmented worms that live in the sea, most freshwater habitats, and damp soil. They are divided into two major clades, the Aurantia, and the Sedentaria. Annelids. Okay. Aurantians. Okay. Most members of this clade are marine. They are mobile, and some swim while others crawl or burrow in the seafloor. Many are predators, while others feed on large multicellular algae. Their body segments have a pair of prominent paddle-like structures called parapodia that function for movement. And sedentarians tend to be less mobile. Some species burrow in the marine soil, while others live within tubes that protect and support their soft bodies. They often have elaborate gills or tentacles used for filter feeding, so these would be like your leeches or your typical earthworms. Ecdysozoans. This clade includes animals that shed a tough external coat as they grow, or they molt. The two largest phyla are nematodes and arthropods, and are among the most successful and abundant of all the animal groups. Nematodes are found in most aquatic habitats, in the soil, and in most tissues of animals. The body is covered by a tough cuticle, and as the worm grows, it sheds its old and makes a new, larger one. Nutrients are transported through the body via fluid. And arthropods have segmented bodies, hard exoskeletons, and jointed appendages. They are completely covered by the cuticle, constructed from layers of protein and chitin. They have an open circulatory system. Deuterostomes. You have your two groups, your echinoderms, slow-moving marine animals. A thin epidermis covers the exoskeleton of the hard plates. Most are prickly from skeletal bumps and spines. Unique to this group is the water vascular system, a network of hydraulic canals branching into extensions called tube feet that function in movement and feeding. So these are your sea stars and sea urchins, or your chordates. These consist of two basal groups of invertebrates, the lancelets and the tunicates, as well as the vertebrates. These are bilaterally symmetrical somates, yeah, with segmented bodies. And then I'm not going to play the crash courses, but there's one for simple animals, so your sponges, jellies, and octopuses, and so on. And then there's one for the more complex. One of them?
Which one do you like best?
I like this one. I hope this works. Yeah, I did, because I didn't do it last time. I said not to enable the outside.
Push escape.
Let's see, what was that one called? Simple Animals for Kingdoms. Maybe Chrome People. Let's do Chrome.
I both know people or dogs that we don't consider particularly sophisticated. We sometimes refer to them as simple or real housewives. But when it comes to truly simple animals, we shouldn't underestimate them, because the animal phyla that we describe as being the least complex actually offer us a vivid way of understanding how animals are structured and also how they evolve. Simple doesn't always mean dumb. Unlike those dullers that we've all met in our lives, animals aren't considered simple because they apparently take things for granted, or they think that reality TV is reality. Their simplicity has to do with their tissue complexity. As you know, almost all animal cells are organized into tissues that perform specialized functions. The more different kinds of specialized cells an animal has, the more complex it is. And this complexity is determined in the embryonic phase. As embryos, most animals either form 2 layers of early tissue called germ layers, or they form 3. By exploring the very simplest phyla from animals with no layers at all, aka sponges, to the most basic 3-layer animals like mollusks, you can see how a not totally amazing sounding change in tissue results in truly fundamental and amazing changes. So the places in the animal family tree where these transitions take place, from no layers to 2 layers, and from 2 layers to 3, are some of the most important benchmarks in animal evolution. Let's start with the very simplest of animals. In the phylum Porifera, the sponges. They diverged from the protists probably 600 million years ago, and not a whole lot has changed for them since then. If you've been paying attention, you've noticed by now that almost nothing that applies to other animals applies to sponges. That's because they're so freaking simple. They can't move. They just hang out and filter water for food like bacteria, while some host photosynthesizing microbes that move off of them. More important, sponge embryos don't have any layers. They just have cells. This means that sponges don't have specialized tissues or organs, and their cells can take different forms. Some have flagella to force water into the sponge. Some are more amoeba-like and wander around distributing nutrients. So these cells can transform into whatever type of cell the sponge needs. For this reason, some scientists argue that sponges aren't even animals at all. They're actually colonies of cells that depend on each other to function. But for our purposes, mainly because they're multicellular eukaryotic organisms that can't make their own food, they still count. And they've managed to diversify into nearly 10,000 different species. So good for them. Things get more interesting with Cnidaria, which include jellies, sea anemones, corals, and hydras. They got a couple of sweet evolutionary breaks that made them animals that you do not want to mess with. First and most important break is that they developed 2 germ layers. You'll remember these layers are called the endoderm, the inside derm, and the ectoderm, the outside derm, and they form a tube that allows an animal to ingest, digest, and get rid of stuff. This makes Cnidaria among the oldest living descendants of the world's first diprolast, which is the common ancestor of all true animals. But still, jellies and anemones and other Cnidarians have only one hole that serves as both mouth and anus, and they don't have any organs. So still, pretty simple. Their second evolutionary break is in their ectoderm, which contains stinging cells called cnidocysts. Think Portuguese man of war. I once stepped on a dead one. It was dead, long dead, and I wanted someone to cut my foot off. It hurt so much. So now we've got 2-layer animals swimming around, able to move and eat and poop and defend themselves. The animal kingdom is just one evolutionary breakthrough away from a huge, explosion. And we can see evidence of this breakthrough in platyhelminthes, the phylum of the soft, unsegmented worms that includes flatworms, planaria, tapeworms, and flukes. Not super handsome, but these guys are a big deal because they're the oldest existing phylum that is triploblastic, or has 3 germ layers. So in addition to an endoderm and an ectoderm, the embryos form a mesoderm. I know it's starting to sound like just another piece of toasted turkey on a club sandwich, but this development changes everything. Platyhelminthes themselves are pretty simple, but a couple of phyla up the ranks, this new layer allows animals to form true organ systems, the ectoderm forming the brain and nervous system and skin, the mesoderm forming muscles and bones, cartilage, the heart, blood, and other very useful stuff, and the endoderm forming the digestive and respiratory systems. And this kind of complexity is only possible because one of the mesoderm's key features, the coelom, a fluid-filled cavity that stores and protects the major organs. It allows the internal organs to move independent of the body wall, and the fluid can provide some shock resistance. Coeloms are where all the action happens when it comes to organ systems, but not all triploblasts have them. From here on, we can assess the complexity of an animal by whether it has coelom. triploblasts. Platyhelminthes have their mouths and buttholes on opposite ends of their bodies, which is awesome for them, but they're acoelomates. They don't have a coelant, which tells us that they're still on the shallow end of the pool, complexity-wise. To give you an idea of how simple, you can cut a platyhelminthes in half, and both of the pieces will happily continue on with their working business. That, my friends, is simplicity. Now, you probably haven't forgotten that I mentioned an explosion a minute ago. Well, I'm not going to taunt you with talk of explosions without giving you one. The Cambrian explosion. Not long after germ layers became a thing, say 535 million years ago, life on Earth was undergoing some pretty terrific and rapid innovations. Over about 10 or 12 million years, about half of the animal phyla that exist today started to appear. It remains the most biologically productive period in history. Think of the most creative and vibrant and dangerous experience and then invite all of Kingdom Animalia to the party, like Burning Man and Comic-Con and Coachella all at once. This is when animals started to look and behave as we know them today. Before the Cambrian, most of the big animals were slow and soft-bodied and ate algae or scavenged. This explosion of diversity brought all kinds of new adaptations, including predatory ones like claws and defensive ones like spikes and armored plates. Shells and mineral skeletons made their first appearances. In fact, the adaptations were so many and so abrupt that in the 1800s, the abundance of fossils from this period was used to argue against evolution. Scientists offer a lot of different theories about what caused this explosion. It was probably a combination of a few of these things. For one, oxygen levels became very high in Cambrian seas, which allowed for larger bodies and higher metabolism. It's also thought that ocean chemistry changed with more minerals becoming available for the production of shells and skeletons. And of course, with more diversity comes more competition and predation, which drove selective pressures on animals to become either better at hunting or better at defending themselves. It's pretty near at the top of my list of places I want to go once I put the finishing touches on my time machine. But for now, we still have many modern animal phyla to remind us of this time of crazy awesomeness. The flukes are cool and all, but things start to get more complex with another phylum of mostly nasty parasites, Nematoda, unsegmented roundworms. These guys are pseudocoelomates, meaning that they have an incomplete body cavity. Unlike a true coelomate, whose body cavity is contained within the mesoderm, pseudocoelomates sort of improvise one between the mesoderm and the endoderm. The vast majority of nematodes live in soil, where they eat bacteria or fungus or parasite plant roots, but humans host at least 50 nematode species, including hookworms, which burrow into our intestines and treat us like some kind of food course. But most nematodes are very, very small. A single teaspoon of forest soil can have several hundred in it. Rotifera, meanwhile, are tiny filter-feeding animals that live mostly in fresh or salt water, though some of them can live in damp soil. There are also pseudocoelomates like nematodes, and although they are way smaller than most flatworms, a big honker rotifera is like 2 inches long, they're anatomically more complex, as they have a stomach, jaws, and a tiny little anus. My favorite fun fact about Rotifera is that many of its species are known to exist entirely of females, and they reproduce through unfertilized eggs. Fossils of vertebrates have been found as old as 35 million years, and in many cases, there's not a dude to be found. Go girls. Okay, so now for some of the big dogs. The phylum Mollusca. Mollusks might be kind of simple, but they're amazing, and some of them are incredibly smart. They take 4 different basic forms: chitons, snails, bivalves, and octopi and squid. Now, I realize it can be hard to see how an oyster and an octopus might be related, but mollusks have some important similarities. One, they all have a visceral mass, which is a true coelom, a body cavity completely within the mesoderm that contains most of the internal organs. 2, they also have a big muscular foot, which takes different forms in each class of mollusk. 3, they have a mantle, which in some mollusks makes a shell, and in others just covers the visceral mass. And 4, finally, all mollusks, except bivalves, have a radulum, or a grasping organ on their mouth that allows them to scrape up food. So chitons are these headless marine animals covered with a plated shell on one side, and they use their foot to move around on rocks, scraping up algae with their radula. You know about bivalves, they have shells that are divided into 2 hinged halves, like clams and scallops. They're filter feeders, so they trap particles of food in the mucus that covers their ears. Snails and slugs are the gastropods. One thing that sets them apart is a process called portion, in which the visceral mass twists to the side during embryonic development, so that by the end of it, its anus is basically right above the head. Most gastropods also have a single spiral shell, and most use their radula to graze on algae. plants. And last, but certainly not least, we have the cephalopods, which are the kings of the mollusks as far as I'm concerned. Cephalopods include octopi and squid, and they are obviously a lot different from other mollusks. For starters, they have tentacles that they use to grab their prey, which they then bite with their beaks and immobilize with poisonous saliva. And the foot of a cephalopod has been modified into a really powerful muscle that shoots out water to help it move and steer through the water. But probably the coolest thing about cephalopods is how smart they are. While a typical mollusk might have 20,000 neurons, an octopus has 500 million. If you just do a YouTube search for octopus, you'll find all kinds of videos of them opening jars and stealing people's video cameras. They're like freaking ocean ninjas. Cephalopods got skills. So remember, simple doesn't equal dumb. There's a lot to learn from our less developed cousins. Next time we'll talk about even more complex animals and what we have to learn from that. Until then, thank you for watching Crash Course Biology. If you want to review anything that we discussed in this video, we'll put a table of contents over on one of my slides. I can never.
Okay.
Yay.
Very good.